Bismillahirrahmanirrahim. Assalamu alaikum ji. In the next couple of videos, we will talk about regression. Mostly, we will focus on linear regression. How do we formulate it? What are the possible solutions of a linear regression problem? How can we cast polynomial regression problem as a linear regression problem? Then we will talk about gradient descent algorithm. And finally, we will conclude this topic, regression, for now, with the concept of regularization. And that what is regularization, what are the benefits, and how do we obtain solution for a regularized problem. Okay, so the outline would be, we'll start with formulating or setting up a regression problem. Then we will talk about this linear regression. We will formulate it mathematically. We will talk about model selection. We will talk about how do we solve this linear regression problem. And then from linear regression, we will move towards polynomial regression. I will also briefly talk about the concept of underfitting and overfitting. And then we will talk about regularization to avoid overfitting. And finally, we will conclude with the gradient descent algorithm. Okay, let's start with what we mean by regression. So regression is a quantitative prediction on a continuous scale. We have seen this before very briefly in the, I think, second module of the course, but here we will formally set up. So the idea here is we have a process, it could be a system, has some input X, and you observe the output Y. So we don't know the process, we don't know the system. That is something we want to model. So given a data sample X, we want to learn about this process or system such that we are capable to predict the possible output Y, right? Okay, here process or system refers to any underlying physical logical phenomena, right? So it could be a model in finance, it could be a biological model. So it's a simple, it's a mathematical abstraction, or it is some phenomena that is mapping you from your input X, multi-dimensional input X, to the continuous variable or to a numerical value Y, right? We can take a step forward and we can zoom into this processor system, right? So in process system, we assume that we have this processor system, and the output of this processor system is given by this functional mapping f of x. So we have this function f that take x as an input, right? And it gives an output f of x. Or we can say f of x is a mapping from d-dimensional feature space to the real space. But we don't have access to this f of x. Instead, this f of x is contaminated by some noise n, right? And this noise, for now, we assume that is additive in nature, right? So what you're getting here, y is f of x plus n. So for input, we cannot observe f of x, but we can observe y. A simple example would be that if you have a linear relationship between input and output, linear means a straight line relationship. And and you're getting these blue observations, right? So because if you take observations on f of x, you take points on this line, right? But you don't have access to this line. So, but you have access to y. So the measurements along on this line are disturbed by, or they are getting variations because of the additive noise in it. Our input x can be a vector or a scalar, and our output can be a vector or scalar as well. So based on this, we categorize regression problems into different categories. For example, when y is scalar, we say we have one variable regression. That means your output is a scalar. If observed output is a vector, we refer to it as a multivariable regression. If input is a scalar, we call it single feature regression. And similarly, if X is a vector, we call it multiple feature regression. So in this course, or in these couple of videos, we will focus on one variable regression. We will assume that the observed output is always a scalar, and but our input can be a scalar, or our input can be a vector. Okay. Before we move forward and formally set up a regression problem, let's look at a couple of examples, real life applications where we encounter the regression problems. For example, if we talk about single feature, it could be something that you want to predict score in the course given the number of hours of effort per week. So input X is number of hours of effort per week, and your output Y, which is a scalar, that is score in the course, right? And the processor system is some phenomena that is modeling your learning, that is modeling your effort to your score. Or it could be, if you want to establish the relationship between the e-commerce sales and how much money you put in for advertising. So again, this is a regression problem. Let's talk about multiple feature. If you want to study, if you want to predict operational efficiency of a machine and given data from sensors, you install different sensors on the machine, and based on the measurement of those sensors, you want to predict, you want to study, you want to analyze the operational efficiency of the machine. You want to model the relationship between operational efficiency and the values you're getting from the sensors. It could be predicting remaining useful life, RUL, of the battery from charging and discharging information. So you have information about charging and discharging cycles of a battery, and you want to predict what is the remaining useful life of the battery. In fact, we are doing research in the department on this topic. We want to estimate sales volume given population demographics or given GDP indicators or climate data, right? Because climate is going to impact your sales volume, or it could be pandemic data. So this is again a regression problem. You have multiple inputs, scalar output. It's a multiple feature single variable regression. You want to predict crop yield using remote sensing. So you have satellites and you're getting data from satellites. It could be images, it could be information about gravity, it could be information about the groundwater, the mapping of rivers. You can fuse all of this information and you want to predict the crop yield in some region or crop yield over some area. Okay. Dynamic pricing or surge pricing by ride sharing applications, right? So these ride sharing applications, for example, Uber, they adjust prices to the changing market conditions. So prices vary depending on factors like location, time of the day, weather, overall customer demand, etc. Right. So they take into account all of these information and they carry out dynamic pricing or surge pricing. Again, this is a machine learning problem in which output is a single variable and input you have multiple features, all of these factors. Okay. You want to rate the condition, right, out of 100, say, that is measuring fatigue or distraction of the driver, and given the video, given you install a camera in a vehicle and the camera is continuously monitoring the driver, and based on and from that video stream you want to rate and the fatigue level you want to measure, you want to predict the distraction level of the driver. Or it could be you want to rate the quality of driving given the data from sensors installed in the car or driving patterns. From that information, you want to rate the quality of driving. Okay. In fact, for these last two problems, these are very active areas at the moment, and we have been contacted by a couple of companies here in Pakistan and also from the US market, that they want to predict, they want to find out the fatigue level of the driver, and they want to find out the quality of driving, because this is very important for road safety. Okay, so these were a couple of examples in which we have shown you the applications of regression in real life. Okay, let's move towards the formulation of regression problem and how do we set up the regression problem. We assume that, as I said earlier, that there is an inherent but unknown relationship between input and output, and that is given by this f of x. And we have, but we don't have access to f of x. We have access to y, and we know what is the input. Or we can say mathematically it is simply given by y is equal to f of x plus n. So in the first slide, I showed you example of linear relationship. If you have some non-linear relationship, so this is f of x, this blue curve, and the measurements on the blue curve are disturbed by noise, so you get these yellow observations. In regression, our objective, our goal is that given these yellow observations, given noisy observations, we want to estimate this unknown functional relationship between input x and f of, in fact, we want to learn f of x as accurately as possible. So this is our goal in a regression problem. Okay, let's talk about what we mean by this as accurately as possible. We'll quantify it very shortly. As an example, if f of x is simply given by a straight line, say 4.2 plus 2.4x, it's a single feature regression. We know that the true relationship or the unknown relationship is a straight line, but when you take observations, you get these yellow observations. And if you stack all of this information in the form, and if you take these observations, we have a first data sample in which we have input x, y, we can have a second data sample, and we can have multiple data samples. And if I use this notation, what we had been following from the very first lecture, that our data set is inputs x1, x2, x3 up to xn. You have n number of inputs, and you have, for each input, you have the observed output y1, y2, yn. Right? Okay, so you have these observations, and what we assume that we have these observations, and we assume that this is our model. So that is relating input x and output y. But I have used y hat to denote the model output, because y hat is an estimate of the functional relationship between input and output of a process. So for some input x, y hat is our model output. If you see, our model output depends on x, and also depends on this theta. What is this theta? So these thetas are, in fact, this theta is capturing the parameters of the model. We assume that our model is f hat x of theta, which is characterized by these parameters. So theta is a vector that contains all of the parameters. And this model, this formulation of model, is capturing two things. The first thing is a structure, that what's the structure, what's the mathematical structure of the model. It could be linear, it could be polynomial, it could be inverse, it could be exponential, it could be sinusoidal. Then what is the structure of your model? And it is also capturing how many parameters in the model you have. For example, you talk about polynomial regression. If you use polynomial to model your unknown relationship, what is the degree of your polynomial? Right? So because degree of polynomial would change the number of parameters characterizing the model. Okay, so we assume that this f hat x of theta is our model that is establishing the unknown relationship between x and model output y hat. And this model depends on the parameters, which are all of them are indexed, all of them are grouped in a vector theta. So y hat is your model output, y is your observed output, and the difference between these two is y minus y hat, right? So it should be a minus here, in fact. So y minus y hat is your error. Okay. And what is the goal here? We want to learn, we want to find these thetas, right? So these parameters such that, so first we want to find the model. And once we find the model, we want to find these parameters for which your model output is as close to observed output as possible. So this model error is y minus y hat. And we want to minimize this model error. Okay, so this will be this was a quick overview about regression. And we now move towards a linear regression. This was so far. So we've not talked about linear regression. We've talked about regression in general. Okay, linear regression. So after KNN, this is a second learning algorithm of the course. We will assume that we have a scalar output, which is a linear function of your inputs. Your input can be a scalar or a vector. So we have a multiple feature, single variable regression problem. Right? This is different from KNN in many aspects. So in linear regression, we will adopt a modular approach, which we will use most of the times in this course. We will start with model selection. After model selection, we will define a loss function. Using loss function, we will formulate an optimization problem, and we will use optimization problem to find the parameters, those parameters for which the loss function is minimized. And then we will talk about different techniques, different methods, different algorithms, which you can adopt to solve optimization problem or minimize loss function. Okay. So let's start with the model of linear regression. We have this data, so x1, x2, xn, where each input is in d-dimensional feature space. Output is a scalar, so y1, y2, yn. So all of these are scalars. In linear regression, we say we chose a model in which output is a linear function of the features. That means output y1 should depend on x1. x1 means the first feature of x1. I can call it x11, x12, and so on and so forth. Right? So model depends on, so each of this input x, so this is in d-dimensional feature space, and we say that each of these x's, x1, x2, up to xd, right? And we assume that output y for this x, this vector x, depends on, it's a linear function of these d number of features, right? So we say we have model is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on and so forth. And if I define a vector theta, which has theta 1, theta 2, theta d, this is my theta vector. So I can write with this using this compact notation as theta naught, right? And this summation can be written as inner product of, or a dot product of, theta with x. So theta naught plus theta transpose x. This is a model. This is a model in linear regression. So this model has a linear structure. So the model parameters are theta naught and these d number of thetas, theta 1, theta 2, up to theta d. So what is the interpretation of theta naught? If you see, theta naught is not scaling, or is simply adding to the linear combination of the inputs. So we say theta naught is a bias, or you can call it intercept, you can call it offset. There are different names given to it. So theta 1, theta 2, theta d. So these weights represent the weights or slope. For example, what's the interpretation of theta 1? Theta 1 quantifies the contribution of x1. Theta 2 quantifies the contribution of x2. Similarly, theta I quantifies the contribution of ith feature xi. Okay, so why do we call it linear? What is linear here? Okay, when you take d is equal to 1, that means we only have one input. X is a scalar, right? Such a case, our model is very simple. Bias, only have one feature, theta would be 1, theta 1x. You can visualize it, right? So this represents a line in okay, so f of x is a straight line because it is given by theta naught is, if you extend this blue line, theta naught is the offset, it should be theta naught, and theta 1 is the slope of this line. If you see, this looks like a linear or straight line. That's why we call it linear. When d is equal to 2, so input x1, x2, and output is f hat of x. If you visualize this in a 3-dimensional space, you get a plane. So this is, along this axis I have x1, along this axis I have x2, and along the third axis I have f of x or y. So we have these black dots as observations, and you're modeling the relationship between your output and your inputs with a plane, with this. Okay. In fact, when this, for any d, this is theta naught plus theta transpose x. So this is a hyperplane in Rd plus 1. Right? So for d is equal to 1, you have a line in 2-dimensional space, and when d is equal to 2, you have a plane in 3-dimensional space. Similarly, when you have d, you have a hyperplane in Rd plus 1. If you choose different theta naught and different theta, obviously you get a different plane. But for given these yellow observations or these black points, how do we find the best line, or how do we find the best plane? For different values of theta naught, for different values of thetas, you get a different hyperplanes. How do we find the best line? What do we mean by best? Okay. So to answer these two questions, we will define a loss function. Right? That loss function will help us in quantifying what do we mean by best. And once we solve it, we will find the best line. Okay. So let's define what do we mean by loss function. A loss function should be a function of model parameters. For input x, if you recall, what was our error? Model error is your observed value y minus y hat. What is y hat? Model output, which is f hat of x theta, right? And if you substitute the linear model here, you get y minus theta naught minus theta transpose x, because f hat of x theta is theta naught plus theta transpose x, right? So this is the model error. It is also referred to as a residual error because it is the difference between observed value and predicted value. So it's a residual error, the difference between y and y hat. Okay, for d is equal to 1, let's visualize this residual error. So we take these yellow points as observations. This blue line is a true unknown function, which we want to model. And we assume that this black line is the fit, which is theta naught plus theta 1x, right? So for some theta naught plus theta 1, you get this black line. So for this x, say you take this x, for this x, your observed output is this yellow. And your model is predicting that this is, sorry, it should be straight line. This is your model prediction. So the difference between these two along y-axis is your model error, is the residual error, right? You can also visualize in the plane, right? So if you have a plane that is fitting your two-dimensional data, so the difference between, the shortest distance between your observed value and your model output is your residual error. Okay. Okay, let's move forward. And for input x, we have error as y minus y hat, or y minus theta naught minus theta transpose x. But for x1, x2, xn, we can define residual error for each of these inputs. So ei would be given by yi minus theta naught minus theta transpose xi, where yi is the ith observed output and xi is the ith input. And we have error for each of i1, 2 to n. So we have n residual errors for each input in our data. We have a residual error, or we can say we have for different inputs you're getting different error. Obviously, for each observation, you will get a different residual error. Okay, so using these errors, we can define different loss functions, right? For example, we can define a loss function like this, right? We have n number of residual errors, right? And we want to map this n number of residual errors to just one numerical value using a loss function. So we define the loss function, which depends on theta naught and theta. These are model parameters. So you square each residual error and you sum you have a sum of square of residual errors. This is termed as least squared error, or LSE. If I divide this by, if I define another loss function in which I have divided 1 over n. So I have a square of residual error. I have summed these squares and I divide by total number of data points. So as indicates, this is a mean squared error, right? We're normalizing by 1 over n, that's taking a mean. If you take a square root of this, right, what you get is root mean squared RMSE. So we have different loss functions, LSE, MSE, RMSE. But the good thing is, So for all of these loss functions, in linear regression, we have a one minimizer. Right? So there is one value of theta naught and theta for which these loss functions are minimized. We choose, okay, let's find out, let's formulate the minimization of this loss function as an optimization problem. So we minimize this loss function, right? This is in fact least squared error, but I have added this factor 1 over 2 here. Right? And this factor is added simply to make the formulation mathematically more convenient, mathematically more easy to follow. Okay. So we have an optimization problem in hand. We want to find the parameters theta and theta naught for which this loss function is minimized. This can be mathematically written, expressed as, if you want to minimize this loss function, and when you minimize this, you will want to find theta naught and theta. Okay. How do we solve it? We can solve it analytically. We can determine theta naught and theta for which the derivative of it is exactly equal to 0, right? Where the derivative vanishes, right? Or we can solve it numerically. Right? In fact, for this loss function, we have analytical solution as well. Obviously, we cannot have analytical solution for every loss function, but for linear regression, for this loss function, we can determine analytical solution. We can use analytical approach to find theta naught and theta for which this loss function is minimized. And after a couple of videos, I will talk about gradient descent algorithm, which we can adopt to minimize a loss function or to solve an optimization problem. Okay, so let's start with analytical approach. I'm going to reformulate this loss function, right? Because I want to reformulate in the matrix vector notation. In this reformulation, I'm going to define a vector that contains all the errors, error for each point, right? So I can write this as half E transpose E, where E would be simply given by E1, E2 to En. And where each EI is Yi minus theta naught minus Xi transpose theta, a residual error for ith input and ith observed output, right? So I think you're fine with this. This is half E transpose E, where E is given, where this is E, and each of the entry of this E vector is given by this. So it's a vector of the residual errors. Okay, I can write this vector E1, E2, En, right? So as Y1 to Y to Yn minus, okay, what's next in our equation? So I'm going to write these n number of errors in a vector form, right? So Ei is equal to Yi, so E1 is equal to Y1 minus I want theta naught. Okay. So I want to subtract theta naught from every Ei. So theta naught does not depend on I. And then we have final term Xi transpose theta. This term depends on I. So I will have X1 transpose, X2 transpose, and Xn transpose. Each of these X1, X2, Xn, you take an inner product with theta. Okay. So this is, in fact, this is equivalent to this. Right? This is a compact way of writing n number of residual errors. I have simply stacked in a vector form. Okay, let's carry out some more simplification. Right? So I'm going to combine these two terms. So I can write y1, y2, yn minus, so theta naught and theta, I have concatenated these two in one vector, right? And I have concatenated this one vector, a vector of ones and vector of my inputs, so matrix of my inputs as I have concatenated these two, and I get this. Okay, if you expand this, what you get is theta naught minus x1 transpose theta naught. So effectively you get the same thing. If I call this vector of all y's as y, and if you see this matrix, what is the size of this matrix? What size of theta? So this theta belongs to RD. This theta naught belongs to R. So this vector has a size d plus 1, right? It has d plus an element. So what size of this matrix X? It would be number of data points n times d plus 1, right? Where d is the dimension of x1 and you have this one additional. Okay, call this matrix X. And we observe that this matrix only depends on your inputs, right? And I'm going to call this vector of theta naught and theta as W, because these are the weights. And that's why I have chosen W to denote this vector. Okay, with this vector and matrix notation, I can write my error, right? So error is y minus xw. Okay, so error is given by y minus xw. How do you interpret this equation? So what is E here? It's a residual error. What is W? The parameters of the model we want to find. Y, your observations. X is a matrix, but X depends on your inputs. So X is constructed from your inputs, right? So these two, Y and X, so they are coming from your data set D, right? So you can have Y in D, you have x1, x2, xn in D, and you can use those x1, x2, xn to construct this matrix capital X. Okay. If I use this formulation of error, I can write my loss function in a compact form. That is half y minus xw transpose into y minus xw. I've simply substituted this error in this equation, and what I get is this equation. Okay. If you see, this is nothing but just a square of the norm of the vector y minus xw, or error. So with this formulation, our optimization problem becomes this: that you want to minimize, you want to find W for which the loss function that depends on W is minimized, and that is simply given by half y minus xw norm square, Euclidean norm square, to be very precise. In fact, this is a very, very beautiful function. It's an elegant function. It is a convex function. It has one global minima, no local minima. When you minimize this, you find one value of W for which this loss function is minimized. If I ask you to visualize this, you can visualize this in one dimensional, right? If you get loss function and you get say W here, for a given Y, for a given X, we change W, right? So you're going to get something like this. It has, and we want to find this value of W, which we write as W star, and this is the minimum value of the loss function. Okay, and the good thing is we can minimize it using analytical approach. To find this W star, or the value of the weights for which loss function is minimized, we first rewrite the loss function as in expanded form. So half y minus xw transpose into y minus xw. And when you expand this, we get y transpose w, right? So y transpose w, so sorry, y transpose y minus y transpose xw, you get this term. And then you have minus xw times minus xw transpose times y, which is w transpose x transpose y. And finally, you have w transpose x w. If you see, each of these quantities is a scalar, right? So y transpose y is a scalar, y transpose xw is a scalar. So w transpose xy is a scalar. And this is a transpose of this. So effectively, because it's a scalar, so these two correspond to the same value. Right? So we can combine these two, and we get y transpose y minus 2w transpose x transpose y plus w transpose x w. Okay, so this is same loss function. I have simply expanded using the formulation of residual error. To further solve this, we need to introduce the concept of a gradient of a function. So this is a function. So loss function is a mapping from Rd plus 1 to R, because W belongs to Rd plus 1. We have W contains 1 theta naught and D number of thetas, the model parameters. And if it's a scalar function, we know we can take derivative and we can find its global minima. But since it's a mapping from Rd plus 1 to R, we will use the concept of a gradient of a function, which is nothing but an extension of a derivative derivative for scalar valued functions. Okay, let's talk about the concept of gradient. You might have seen this before in some course, but as we're not assuming that you have seen this before, I will quickly explain, I will quickly introduce the concept of a gradient of a function. For a function f of x that maps x to Rd to R, so we have a function f that is mapping from Rd to R, we define a gradient, which is in fact a directional derivative with respect to as this. It's nothing but just a vector of partial derivatives. So f is a function of a vector x, which in fact, so f is a function of x1, x2, say we have taken x in Rd. Let me write cleanly. So f is a function of x1, x2, so on, xt, right? You take the partial derivative of f with respect to x1, you get the first component of gradient. You take derivative of f with respect to x2, you get second component of gradient. Since f is a mapping from Rd to R, so your gradient would be a vector in Rd. So how do you interpret this? So what is the first component? Partial f over x1. Oh, hang on, it should be partial f over partial x1, partial x2, and partial xt. I will update this in the notes, my apologies. Okay, the first component, partial f over partial x1, that is quantifying the rate of change along the rate of change of a function with respect to x1. Similarly, partial f over partial x2, that what's the rate of change of a function with respect to x2. So gradient can be interpreted as it is quantifying the rate of change along different directions, or rate of change with respect to different variables x1, x2, xt. Okay. Okay, and to further strengthen this concept, let's take a couple of examples. We take a very simple example. So we have function of x. For some a, you get an inner product of a with x. Right? So this function takes input x and returns you the inner product between a and x. If I ask you to take derivative to find gradient of this, how would you find it? Right. Let me expand this first. Right. I can write x transpose a as x1 a1 plus x2 a2 and so on xd ad. Okay. So what is the first derivative? What is the derivative of this with respect to x1? a1, right? So the first entry of gradient would be a1, second entry a2, and so on and so forth. Or you can say gradient would be simply given by a vector a, right? Let's take another example. F of x is x transpose x. In fact, this is a function that is giving you square of Euclidean norm of x. That's inner product of x transpose with x. Okay. How do you find gradient? Let's expand this. What is x transpose x? x1 square plus x2 square plus x3 square and so on and so forth. When you take derivative of this with respect to x1, what do you get? 2 times x1. All of terms would be 0. When you derivative with respect to x2, you get 2x2. And then you get 2x3 and so on and so forth. Or you can say the gradient would be simply 2x. Right? If you extend this and we take a function that is x transpose px for some matrix p. This is in fact a weighted inner product. Right? Instead of x transpose x, you have introduced a matrix p that is weighting your inner product. Maybe you can try and you can find derivative gradient of this x transpose px. But if you trust me, if you extend this, if you combine these two, in fact, you get 2 into px. So this would be the gradient of x transpose px. This is all we need, in fact. If you understand these two examples, if you know the gradient for these two examples, this is all we need to solve for a loss function we have. Okay, let's move forward and come back to the loss function. So this is, we reformulated the loss function. If we take derivative, if you take gradient with respect to w, what do you get? The first term would be vanished, 0. Right? What about second term? So you have w x transpose y. If you treat x transpose y as one vector, it's a vector, right? X transpose y as one vector, and you take derivative with w, what do you get? X transpose y as a gradient, right? So for this term, you get 0. For this quantity, you get this. And this is w transpose x transpose w. If you use the previous example and you treat x transpose x as one matrix, say P, you get 2 times the same matrix into w. Right? This is the gradient of the loss function with respect to w. And to find w, we substitute this equal to 0. And when you substitute equal to 0, you get x transpose xw is equal to x transpose y. And from here, I can recover w as x transpose x inverse x transpose y. Obviously, the assumption here is this matrix x transpose x is invertible. So inverse of this exists, right? So what is the size of this matrix? What is size of x? Do you recall? The size of x was? Okay, what is the size of y? The size of y is n times 1, right? And what is the size of x transpose? X transpose would be d plus 1 times n. So x transpose x would be d plus 1 times d plus 1, because our w is in d plus 1. So d number of coefficients, theta 1, theta 2, theta d, and you have theta naught as bias. So in total we have d plus 1 variables. If you have too many data points, so you expect this x transpose x to be invertible. And we will see later in the course that if this is not invertible, how do we find this w and how do we solve? How do we move from here to this stage? Okay, so we have determined the weights for which the least square error, mean square error, or the root mean square error, or the norm of the residual is minimized. So due to this, this solution is referred to as a least square solution because it is minimizing the least square error. So we started with the linear regression problem. We assume that we know the structure of the model, that there is a linear relationship between input and output. The number of parameters we wanted to learn would be the dimension of the feature space plus 1, d plus 1, right? We formulated our loss function using the definition of residual error, and using residual error we defined loss function, and minimization of loss function we casted it as optimization problem, and we have obtained the solution of optimization problem using analytical approach. So in fact, as I said earlier, so linear regression is one of the handful of models for which we can obtain solution analytically. And we will shortly learn an algorithm, gradient, so-called gradient descent, to solve optimization problem numerically. Okay, so we stop here. In the next video, we will start with the concept of polynomial regression. And in fact, we will reformulate polynomial regression problem as a linear regression problem. And this will help us to use the same machinery we have developed here to solve a polynomial regression problem.